Good morning to the people in my physics classes on today, the 31st of Hiri Tuti Kōka, which is August 2021. Just clicking along here a little bit. What I'd like to do today is look back at the homework that is now due. There was some which I've given prior to the lockdown. Revisit the Scottish flag helper for circuits and parts of circuits. It works in parts of circuits as well. I want to give you some new homework, see what the work is, and then I'm going to show you how to do the hardest question, pardon me, in that homework. Then I'll set some new homework, and I'm going to avoid setting a due date. Instead of putting too much pressure on, I'll let you work on that as you go, and we will get it done when we come back, hand it in and get it marked when we come back to school. That'll be quite nice. I think that takes some of the pressure off some people, because some folk are struggling, and if you're finding it easy, hand it in by taking a picture of it. And if you are struggling, we'll sort it out later on. Cool, moving along here. This is the homework that we've had ongoing. Basically, all of waves is now due, which is really important because when we come back, we'll be doing the class test in place of the derived grade exam. Moving along, don't need that. Now, last couple of lessons I've taught you this, which is the Scottish flag way of learning voltage and current in series and parallel. I remember current and series is the same, and then the diagonals have identical words, same and split. Moving along. The new homework I'm going to give you is on pages 148 and 149, and that is coming up shortly. But this one here is the hardest question. It's question number 6 on page 149. Excuse me. I'm going to talk you through the step by step how to solve this question. We've got to find the current through each lamp and the voltage across each lamp. So first of all, I want to talk about conventional current. Conventional current is current that by convention goes the opposite way of electrons. It's a horrible idea, and it's an inherited stuff up from days gone by, but we'll have to live with it. So even though we know electrons come out of the negative side and round through this way to the positive side, we pretend that conventional current comes out of the positive side round through to the negative side, and that positively charged things are moving. I hate it, but we have to live with it. And there's a reason for it later on. I'll explain how it came to be. But for now, we'll live with it. So conventional current comes out of the positive side, and there's 6 amps flowing out of here. And what I'm going to do is it comes through to here, and step by step, the first one. Voltage in parallel is the same. That was one of the steps we had before. And so therefore, if there's 8 volts across this bit, there'll be 8 volts across this bit here. And I can say that here. And the voltage in series is split, so the voltage across B is 8 volts. So therefore, the voltage across C and D is going to be 8 volts. But because they're in series, it'll be 4 volts each. So we got a total of 4 volts there plus 4 volts there makes 8 volts in series, because there's 8 volts in parallel with them, which is kind of useful. Moving along. The current through C and D is half of what goes through B, because it's twice as hard to get electrons through here. And also, if there's only 4 volts across this lamp here, then we're only going to have half the current there. So 2/3 of 6, the 6 amp splits. Current in parallel is split. 4 amps goes through there, and the remainder 2 amps goes through there, because there's only 4 volts across this one, 8 volts across there, so only half of the current, because they're proportional to each other. As one goes up, the other goes up. And that makes sense, because then there's 4 volts there, 4 amps through this, 2 amps through these, and 6 amps make it through and come out this side. Then C and D are in series, so they also get 2 amps, and the D also gets 2 amps. Now, moving along, voltage in series is split, so the 28 volts supplied here gets shared as 12 volts across that one, we'll get to it, 8 volts across here, which leaves, so 12 and 8 makes 20, which leaves 8 volts across this, across this big, I'm in trouble here, across this big combo here, there's 8 volts across it. Voltage in parallel is the same, so the voltage across this arm is equal to the voltage across the GH, which is equal to the voltage across IJ. That's all equal to 8 volts, because 8 volts here, plus 8 volts here, plus 12 volts here, makes it 28 volts supplied. Cool. That's really useful. Voltage in series is split. So if there's 8 volts across this lot, there's 4 volts there and 4 volts there. And 4 volts for each of these ones here. Current in parallel is split. So if 6 amps comes in here, and these are all identical, 2 will go through here, 2 will go through here, 2 will go through here. So they all get 2 amps. The lamp at A gets 12 volts, and I just moved my face out of the way. And the current in series is the same, so it gets all 6 amps. Summary on the next page, here we go. So you can freeze this if you like. The voltage across is 12, 8 and 4 for everything else, 6, 4 and 2 for everything else, and the comparison volts for each amp, which I'm going to get into the next lesson, is 12 volts for 6 amps is 2 volts for each amp, 8 volts for 4 amps, 2 volts for each amp, 4 volts on 2 amps, 2 volts for each amp. And I think that's a good place to stop. It's a bit longer than normal. Sorry guys. Have a grand day, fellas.